Hey everybody, today we're going to work on triangle properties lesson number 4. Now in the previous lesson, properties 3, we were able to do perpendicular bisectors, and those met at a place called the circumcenter, and we were able to draw a circle around the triangle, and that point, that circumcenter, was the center of the circle. We also did angle bisectors, and they met at a place called the incenter. And then that would mean if you inscribed a circle inside the triangle, then that point would be the center of it. Today we're going to learn about two new ones here. We're going to learn about medians and altitudes, and we're going to talk about what that actually does. So we are going to draw our first figure. We have point D, point E, and point F. So this is going to be a fairly large triangle for our example, which is good. That's kind of what I was going for here. We've got D, E, and F. We're going to connect them, and then we're going to follow the directions. Now, to draw a median, what you have to do, a median is different from the others because the median starts at one vertex, and then after that, it goes to the midpoint of the opposite side. Now, in this particular case, I'm going to take this first midpoint right here, and I'm going to just eyeball it here. So if we've got a length across of 10, that means the midpoint would be halfway down, so it would be 5 and 5. I'm not going to take a long time to go over how to find the midpoint here, because in this particular lesson, you will probably be just fine just counting squares and figuring it out for yourself. It will not be that difficult. Now, early on in lesson number 1, we talked about mid-segments, about how if you go midpoint to midpoint, you would get a mid-segment. And so a lot of students try to work ahead as soon as they see this picture, and they just start drawing mid-segments. That's not what I want you to do. A median is when you go from one vertex to another midpoint. One vertex to another midpoint. One vertex to another midpoint. And just like these other ones, it's absolutely crazy, but it's true. Sure enough, they all met at the same place. I believe for the sake of conversation, I'm going to call this point C. All right, so let's look at one of these lines in particular, okay? Let's just look at the first one that we drew. It doesn't really matter which one we look at, but I just want you to look at one of them. That line right there, as I said, is called a median. And all three of them did come together at a place called the centroid. Now, that's kind of a weird word. It reminds me of old video games. There's an old video game called Metroid. So if you combine median and centroid, you get Metroid. That's just a cheesy thing that I do. It might not mean anything to you, but it's just one way that I remember these things. There is a rule that applies to this. And this particular rule, it's a little long, but I don't think you'll have too much trouble with it. There's actually a couple of different ways to look at it. So I'll write it out for you, and then we will talk about what it means. So it says the medians of a triangle are concurrent at a point that is 2/3 the distance from each vertex to the midpoint of the opposite side. If that's a lot of writing and you need to stop the video for a second, go ahead, but I'm going to move on and talk about what that means. So let's look at that example right here. So the entire median went from E to X. Now, if you look at the distance from E to C and then the distance from C to X, you can kind of tell that they're not the same distance. You can kind of tell that EC is longer than CX? Well, it turns out it's actually twice as long. It turns out this is 2/3 of the whole thing, and this is 1/3 of the whole thing. And that works for every median every single time. So if we looked at another one here, this would be 2/3 of the entire length, and this would be 1/3 of the entire length. One more time, you could go over here and you could say this is 2/3 of the whole thing, and this is 1/3 of the whole thing. Now, the significance of that, let's say I told you this whole thing was 15. Well, 2/3 of 15 would be 10, and 1/3 of 15 would be 5. Or let's say I told you this whole thing was 18. Then that means this would be 12, and this would be 6. Or let's say I told you this whole thing was 9. 2/3 of 9 is 6, and 1/3 of 9 is 3. Now, those numbers are all completely made up. Those aren't the actual measurements, but I'm just trying to give you an example. Now, in fact, if you take one closer look, you can actually see the big piece is always twice as big as the little piece. So there are a couple different ways that we can look at these numbers. I think they're helpful to kind of compare and look at that way. As far as the 2/3 relationship goes, if you look at the picture, you could see that DC, the distance from D to C, is going to be not DZ, but 2/3 of DZ. So let me explain that real quick. Let me put this down here. DC, as in this part, is going to be 2/3 of the whole thing. Okay, and that 2/3 relationship applies all 3 times, so to all of the medians. So we could use that relationship again, and we could say that EC is 2/3 of that whole thing. And last but not least, we could say, if we looked at the third one, we could see that the distance from F to C is 2/3 of that entire distance as well. So it's a 2/3 relationship, 2/3, 1/3. And if you're only looking at the parts, you could say that one part is twice as big as the other. All right, now our last example, just to save us some time, I already drew it. Now you can stop the video again if you want, just to make sure you get that jotted down. We want to make sure that triangle looks just right. In this particular case, we are going to work on a 4th type of line, the last line we're doing here, called an altitude. So yesterday we did 2, today we're doing 2, or whenever it is that you did the previous note sheet. Now, altitudes meet at a place called the orthocenter. Now, when I think about what it means to think of the word altitude, the thing that I think of is height. You know, the altitude of a city is, let's say 3,000 feet above sea level. That is basically saying that city is 3,000 feet higher than just a regular sea level, as in normal piece of land. So when I think altitude, I think height. So real quick, it's not hard to visualize an altitude, especially if you have a base that is flat. All you have to do is think of it as height. So back in the day, you used to do a formula for the area of a triangle, and you used to do 1/2 base times height. Think of altitude as height. Now, a technique that I would recommend in this case, I'm going to demonstrate for you here. I have it ready to go. Now, I want you to rotate your figure so that you have a different base. Okay, so rotate your figure until it looks something like this. And then what we're going to do is we are going to draw the height again. Okay, so you're going to rotate your figure until you have a different base, and then you are going to draw the height again. Because again, altitude is basically just the same idea as height. Now, obviously, there is a mathematical way you could do it. Height is always perpendicular. You know, if you're measuring your height, you're going to stand up as straight as possible. You're going to be perpendicular to the ground. You can't just stand crooked and get an accurate height. You have to be perpendicular to the ground. You have to be standing straight up. So we've got a second one. Okay, then after that, I want you to rotate your paper one more time until you have a new base. And at that point, I would want you to draw a new height. So in the end, your picture should look something like this. Okay, so let's go back up to the work that we were doing earlier here. And I can add those other two in pretty quickly. That won't be hard to do. Once that happens, once you've got that down, you should be able to see that all three of them crossed at the same point. So once again, just let me add what we discovered as we were rotating our papers around a little bit there. Boom, boom, boom. There you go. All right. So it turns out, just like in the other cases, the three of them did cross at the same point. In this particular example, that point was 2, 4. Now, the one thing that you need to know that we haven't talked about yet with altitudes, and I am not going to spend a lot of time talking about it right now, I'm just going to make up an example here. If you are doing the altitude of an obtuse triangle, as in you're trying to figure out the height of an obtuse triangle, you have to go perpendicular until you hit the ground, even if you don't actually touch the triangle itself. So in this case, the altitude, as in the height of this triangle, would be right here. So even though it's not inside the triangle, it still counts because you're thinking in terms of height. What is the height? That matters because just like with perpendicular bisectors, if the triangle is obtuse, the altitudes will meet at a point that is outside the triangle. Now, ultimately, what the picture here would look like would be something like this. You'd have an altitude here. You'd have one here. And then you would also have one here. And they would meet outside the triangle. It's a pretty cool picture once you draw it out, but I just wanted to give you a sense of that before we did our final theorem and we quit for the day. So the last theorem of this lesson would be Theorem 5.9, which is the concurrency of altitudes theorem. Now, a lot of people are getting caught on the word concurrency. Being concurrent, I concur means I agree. So basically, whenever you hear a point of concurrency, it's a point where they all touch. It's a point where they all agree. So we've got ourselves the concurrency of altitudes theorem. And this theorem is pretty lame, I'm not going to lie. The lines that contain the altitudes of a triangle are concurrent. That's all it says. It's not saying that there's a special rule. There's no 2/3, 1/3 deal. It just says eventually they're going to meet. In the examples that we did earlier, they met right here. In the obtuse example, we had to continue them on farther. So we weren't just talking about the altitude itself, but we were also talking about the line containing it. We continued them further, and we found out that it met on the outside. That does happen. Again, it happens for perpendicular bisectors, and it also happens for altitudes. All right, our final review here. The point of concurrency, where do they meet? If it's a perpendicular bisector, they meet at the circumcenter. If it's an angle bisector, it's the incenter. And then the two that we just did, medians meet at the centroid, and altitudes meet at the orthocenter. So that's a lot to deal with. These last two note sheets, we've covered quite a bit. So make sure you stop the video, jot these down, and collect your thoughts before you quit. Thanks a lot. I'll see you next time.